All right, so today we're going to finish section 9.2.2, and we're going to first start by looking at complex conjugates. And what does that mean? So first thing, it says in numbers 1 to 4 below, calculate the sum and product of each pair of complex numbers. So again, for the sum, that means we're going to add them together. So I'd have 2 plus I plus 2 minus I. So when I add those like terms, 2 plus 2 is 4, I minus I is nothing, so I get just 4. So therefore, adding these two complex numbers together gives me a real number. And then when I find the product, that means I would do 2 plus I times 2 minus I. 2 times 2 is 4, because I'm going to have to FOIL this now, minus 2I plus 2I, and then minus I squared. And so that will give me 4. Negative 2I plus 2I is 0. Minus, and we know I squared is negative 1. And so 4 minus a negative 1, that minus a negative 1 can be plus 1, which would give me 5. So again, I would get a real number out here. I'll do one more with you guys. All right, for the sum here, I would do 3 minus 5I plus 3 plus 5I. So 3 plus 3 is 6. Negative 5I plus 5I is 0, so I get 6. And then my product, three minus 5I times 3 plus 5I. So 3 times 3 is 9. 3 times 5I is plus 15I. Negative 5I times 3 is negative 15I. And then negative 5I times 5I is negative 25I squared. So the 15 and the negative 15I, they cancel. And I have 9 minus a negative 25. So 9 minus hold on a second here. 9 minus 25. And then I have I squared is equal to negative 1. And then negative 25 times negative 1 is plus. So I'd have 9 plus 25. So we would be at 34. All right, so I want you to try and do the sum and product for 3 and 4. So what did you notice every time that you found the sum and product? You should have noticed that you got a real number out. And again, these were called complex conjugates. So if you notice what was happening, this was 2 plus I and then 2 minus I. 3 minus 5I, 3 plus 5I. Negative 4 plus I, negative 4 minus I. And again, every time we multiply those together, we got a real number out. So this problem says, what complex number can you multiply 3 plus 2I by to get a real number? So if you kind of looked at all these, the real number part was always the same. The imaginary number part was the opposite sign though. Okay, so we're going to keep that 3, but we're going to make it minus 2I. And then it says, what happens when you multiply negative 4 plus 5I times negative 4 plus 3I? So if we multiply this out or FOIL, we have 16 minus 12I minus 20I, and then plus 15I squared. And that would give us 16 minus 32I plus 15I squared. And we know I squared is negative 1. And so that would give us 16 minus 15, which is 1, minus 32I. So that is not still a complex number. It's not a real number. So the only way we can get real numbers out is by multiplying, keeping the real number part the same, and making the imaginary part opposite sign. So what complex number can you multiply a plus bi to get a real number? Yep, that's right, a minus bi. So the real number part stays the same, but the imaginary part is the opposite sign. And that's what we call complex conjugates. So complex conjugates are a pair of complex numbers, pair meaning two. So these are complex conjugate, two complex numbers, where the real number is the same. So like here we had 3 and 3, that's the same. But the imaginary parts have opposite signs. So if you look here, opposite signs, we had a minus 5i and a plus 5i. Whoop. Minus 5i plus 5i. The product and sum of complex numbers create real numbers, as you saw in numbers 1, 2, 4 right here. So examples of complex numbers, again, you can create anything, 6 plus 7i, and then 6 minus 7i. As long as the real number part's the same, opposite number, imaginary numbers, opposite sign. Those are complex numbers. All right, and then we're going to look at how do you divide complex numbers. So what happens if there's an I in the denominator? So you cannot leave a complex or imaginary number in the denominator. It's not simplified. So the first thing you're going to do is you are going to multiply the numerator and denominator by the complex conjugate of the denominator. This will make the denominator become a real number, which is what we want. Denominators can have to be real numbers. After you do that, then you're going to FOIL and or multiply depending on the problem, and then simplify. So we see some examples here. So I have 3 divided by 2i. So there's no real number part of this, or the real number part is really a 0, if you think of it that way. So the real number would still be 0. So the complex conjugate to this would just be negative 2i, because it's like 0. This is like 0 plus I, and then we would run 0 minus 2i. 0 plus 2i, 0 minus 2i. So really we're just multiplying by negative 2i, top and bottom. So when I do that, 3 times negative 2i is negative 6i. And then 4i times negative 4i is negative 4i squared. And again, we know that I squared is equal to negative 1. So we'd have negative 6i divided by negative 4 times negative 1, or negative 6i divided by 4. Last thing you want to do is just simplify if needed. We can divide each of those by 2. So negative 3i divided by 2 would be our most simplified answer. All right, so here's where we have a binomial in the denominator. So this is where we would multiply by the complex conjugate, as always. So our complex conjugate now would be the real number part stays the same, 2, but minus I. And then times 2 minus I. Again, you're multiplying top and bottom by that complex conjugate. And now I'm going to have to distribute here on the top. So that would give me 6 minus 3i. And on the bottom, I'm going to FOIL. 2 times 2 is 4. 2 times negative I is negative 2i. I times 2 is positive 2i. And then I times negative I is negative I squared. So that gives me 6 minus 3i divided by, I have 4. Negative 2i plus 2i is 0 minus I squared. And we know I squared is negative 1. And so again, we want to end up with a real number in the denominator, which we will have. 4 minus a negative 1 is plus, so 4 plus 1 is 5. And the only other thing you'd want to do is see if you can divide. And if I tried my heart method, I can't divide 6 by 5, I can't divide 3 by 5, so you can just leave it as such. All right, last one we're going to do together. Again, we're multiplying by the complex conjugate here for number 3. So I'm multiplying by 3 plus 2i over 3 plus I, I'm sorry. The real number part stays the same, imaginary part's opposite sign. So 3 plus I on the bottom and 3 plus I on the top. And so now I'm actually going to FOIL the top and the bottom. So 4 times 3 is 12. 4 times I is 4i. 2i times 3 is 6i. 2i times I is 2i squared. On the bottom, 3 times 3 is 9. 3 times I is plus 3i. Negative I times 3 is negative 3i. Negative I times I is negative I squared. All right, we got a little simplifying to do. So we have 12. 4i plus 6i is 10i. Plus 2, and we know I squared is negative 1. On the bottom, 9 plus 3i minus 3i. Those cancel. Minus, and I squared is negative 1. So we would end up with 12 minus 2 is 10 plus 10i all divided by 9 minus a negative 1 is plus, so 10. So now I would do my Hart method, divide each by 10. 10 divided by 10 is 1 plus 1i, or 1 plus I. Final answer. All right, try doing these 3 on your own. And last but not least, we have a factoring of sum of perfect squares. So if you remember difference of perfect squares, last thing we're going to look at is factoring sum of perfect squares. And if you remember earlier in the year, we factored difference of perfect squares. And I always told you before that we could not factor sum of perfect squares. Reason being, if you look at a graph, so if we look at factoring x squared plus 9, those are both perfect squares, they're being added. But if we sketch a graph of that, of y equals 9x squared, this would be a parabola moved 9 units up. Does it actually touch the x-axis? It does not, which means it's not factorable. We'd have no real roots. So now we can factor this, but we're going to factor it using complex or imaginary numbers. So what we're going to do is we're going to rewrite the expression as subtraction. So instead of x squared plus 9, we're going to think of it as x squared minus a negative 9. And then if you remember difference of squares, the formula for difference of squares was you factored, or you made your 2 sets of parentheses. You took your square root of the first, so the square root of x squared is x and x. We took the square root of the second term, so now our second term is negative 9. So the square root of negative 9, remember, would be the square root of 9 times the square root of negative 1, which would give us 3i. So I'm going to put 3i here and 3i there. And then remember, when we do difference of squares, it's always 1 plus and 1 minus. Now you might say to yourself, well, how do we know this works? Well, if I FOIL this out, I should get x squared plus 9. So let's see. So if I do x plus 3i, so this is a check. X plus 3i, x minus 3i. If I FOIL this, x times x is x squared. X times negative 3i is negative 3i. 3i times x is plus 3ix. And I apologize. When I did first is x times x is x squared. X times 3i, negative 3i is negative 3ix. 3i times x is positive 3ix. And then 3i times negative 3i is negative 9i squared. So as we keep going here, I have x squared, then negative 3ix, the positive 3ix, they cancel. And I have minus 9, and I squared is negative 1. And that would make it x squared plus 9. So it does check. So your formula for sum of perfect squares, where you have a perfect square plus a perfect square, would be, we took the square root of the first, so it would be a and a. And then we had to take the square root of the second term, but because it's plus, we had to write plus bi, and then be plus bi and minus bi. So you're still taking the square root of the second, but you're putting that I at the end. So for example, x squared plus 4 They're both perfect squares. They're being added. Remember, you really kind of want to think of it like this. X squared minus a negative 4. So when I do difference of squares now, x and x, square root of x squared is x. Square root of negative 4 is 2i. And you always have opposite signs. So that's what we were talking about here. Square root of 4. So we put 2i. We'll do one more together for number 2. Again, if you want, think of it as 4x squared minus a negative 25. And we have square root of 4x squared is 2x. Square root of negative 25 is 5i. And then 1 plus, 1 minus. All right, try number 3 on your own. And you should have ended up with 3x plus I, or 1i, and 3x minus I, or 1i. All right, there we have it.